This is the 12th lecture of the course MTH 204A for section B. Recall that in the last lecture we were looking for the stable orbits and stabilizers under the actions of G on itself. So, given a group G, it acts on itself there are 3 standard actions. One is left, another one is right, and the third one is conjugation. Okay. Now, it is easy to see that this map x goes to x inverse actually establishes an isomorphism between left and right actions of G on itself. So, therefore, we do not need to really consider both of them. So, we will simply forget the right one unless it becomes necessary to consider that. So, we will mostly consider the left action of G on itself, and together with, of course, we will consider action of G on itself by conjugation. So, as I said that we can simply forget the right action because that is exact isomorphic to left action. Okay. So, now let us talk about the action of G on itself from this left action. So, in this left action you can see that the action is transitive. And the stabilizer of every point is trivial. Now, the left action of G on itself induces an action of G on the set of all cosets. So, in fact, let me put it in this way: given a group G and two subgroups H and K, so one can consider the action of H on G mod K. So, how is this action happening? So, H comma A K goes to H A of K. So, we will and we have already also seen that this action need not be transitive, and the stabilizer of a coset is basically, so that means H A K is A K. So, A inverse H A belonging to K, hence H belongs to A K A inverse. So, thus the stabilizer is H intersection A K A inverse. This is what we have already seen. We will consider two special situations of this. So, the special case 1, when H is equal to K and the index of H is the smallest prime dividing order of G. So, it should begin with a finite group G, two subgroups H and K. Should begin with a subgroup. So, G is a finite group, H is a subgroup whose index is P, which is the smallest prime dividing order of G. Then we consider the action of H on G modulo H itself. Now, the situation is that what happens to this action? So, the coset H is a fixed point under this action, and therefore, this action cannot be transitive. Okay. So, what about any other non-trivial orbit? Does there exist any non-trivial orbit? So, observe that if O is a non-trivial orbit, under this action, then so what about the order of O? So, it has to be less than P. So, if non-trivial means it will be, So, the order will be simply this. Now, by orbit stabilizer theorem, the order of an orbit divides the order of the group. So, order of H, which also divides order of G by Lagrange's theorem. So, what does that give us? So, therefore, we see that since this is having order between 1 and p, strictly between 1 and p. So, thus we obtain that there is a prime smaller than p which is dividing order of G, and that cannot happen. So, therefore, the possibility that there is a non-trivial orbit that has been now ruled out. Okay. So, once that possibility is ruled out, so what do we obtain? We obtain that for every A in G, A in G, AH is a fixed point. Under the action of H on G modulo H. So, so fixed point means its stabilizer is going to be whole of H. So, stabilizer of it must be whole of H, but on the other hand we have seen that in general the stabilizer is this intersection. So, therefore, what we obtain is here. So, A H A inverse, right. So, yeah, so A H A inverse intersection H. So, what does that give us? That gives us that. So, the intersection is H. So, the intersection becomes H. So, when does that happen? It happens when H is strictly contained between AH A inverse, H contained inside AH inverse. Okay. Now, since both of they have the same number of elements because they are finite groups, so finite subgroups, so we must have equality. So, this shows that AH is normal. So, which is equivalent to say that H is normal in G. Okay. So, that is what we have proved is if for a finite group, if a subgroup has index the smallest prime dividing the order of the group, then the subgroup has to be normal. Okay. The second instance which we have to talk about is very important. So, consider that G is a finite group whose order is p to the, let us say some p to the power k times m, where p is a prime. And this is the highest power of p that is dividing order of G, so that is p does not divide m, and also let H and k be two subgroups of G having order p to the power k. Okay. Having order p to the power k. Now, what we do is, as expected, we consider the action of, so action of k on G modulo H. Okay. So, what happens to this action? So, it is easy to see that this action indeed has a fixed point. Why? Because we just write down the class equation. So, the class equation just says that, so number of fixed points plus number of fixed points plus the non-trivial orbits, some or let me non-trivial orbits, well, or some order of, right. So, let us try to see what is happening is k has order p to the power k has order p to the power k. Okay, sorry, yeah, this subgroup k has order p to the power k, and for each non-trivial orbit its order has to divide the order of p, since they are non-trivial. So, all these terms appearing here are divisible by p. So, therefore, this is divisible by p if and only this is divisible by p, but this is not divisible by p because p does not divide m. Therefore, this quantity is not divisible by p, thus it cannot be 0. Hence, that means there exists A in G such that there is A in G such that for every k, Ka of H is A of H. So, yeah, so that is there is a fixed point, there is a fixed point for the for this, yes. Now, yeah, so there is a fixed point for this. Now, recall that for any general action, if two points are in the same orbit, so for any general action of G on x, so if Gx equals to y, then the stabilizer of y in G is nothing but the conjugate of the stabilizer of x by this G, right. That is easy to see, which you have already seen. Now, let us come here. So, in the action of G on G modulo H, so the stabilizer of H was, so in this action the stabilizer of H was, H itself, okay. So, therefore, the stabilizer of any stabilizer of this H is going to be a conjugate of H stabilizer of AH in G is going to be the conjugate of H, okay. And we have already seen that AH is a fixed point under the action of K, that is this. So, this implies that K has to be contained inside AH A inverse, right, because we have already proved that K stabilizes, every element of K stabilizes AH. So, therefore, it contains inside that, and again H and its conjugate having the order same order p to the power k, k is also having the same order, therefore, we obtain the equality. So, thus what we have proved is, in such a situation, if H and K are two subgroups with this order, that is the maximum order of the maximum power of the prime dividing order of G, then H and K must be conjugate, okay. We get it as a consequence of action and consequence of action on the space of cosets, and of course, we then exploited class equation. So, this fact is called Sylow's second theorem. In fact, in this course we will look at Sylow, the three celebrated theorems of Sylow. So, this is the second theorem, Sylow's second theorem. Okay. In order to see Sylow's other theorems, so then we have to consider a different action, which we will do now. So, note that this is an observation, like we have seen that the action of G on itself by left multiplication induces an action of G on the space of cosets. So, similar to that, somewhat similar to that, we can observe that the action of G on itself by the left multiplication indeed induces an action of G on the set of all, on the power set of G, set of all subsets of G, okay, the power set of G. So, in fact, more generally what you can see is, more generally, if G acts on a set X, then G indeed acts on the power set of X in the most obvious way. So, each G and A goes to GA. How is GA defined? It is defined in this way, okay. Here this is, so this is, so this is nothing but the action. So, yeah, so this is from the action of G on X. So, for a whenever G acts on a set X, it acts on its power sets, and yeah, it acts on its power sets. But in this lecture, or since in general this action does not give us something interesting, whereas the action of G on the power set of G by left multiplication indeed yields something very influential. So, as I said, that since this is not in general, since this is not giving us anything substantial, so we will not get into this. Rather instead we will stick to the this for special case. So, let us do that. So, G acts on the power set of G by left multiplication, by left multiplication. Well, in fact, furthermore, that if we have a subgroup, K is a subgroup of G, then K also acts on the power set naturally. Okay. Now, if A is a subset of G, then for there is no guarantee that every element. So, if I act by the elements of K on A, then some elements of K might be moved outside A. So, in order to avoid that, what we can do is we can consider stabilizer of A inside K. So, let us denote that for the time being by Ka. Okay. So, thus now Ka acts on A by left multiplication. So, again let me tell you that we cannot take whole of G, or we cannot take whole of K, because K might push some elements of A outside A. So, but here now it is fine. So, now what we obtain is if G is finite, then what we obtain is, again we will write down the class equation. So, what are the orbits? So, under left multiplication, orbits are the cosets of the right cosets. So, basically this will be, the class equation tells us it is of the form for some A's, okay, for some A's, so that K so that this cosets form a partition of A. Okay. Now, since each right coset has same number of elements as that of Ka, so from here it follows that Ka divides order of A. Okay. So, this kind of argument you have seen earlier when we are proving Lagrange's theorem from group actions. Indeed, this is a generalization of that. To see that, what you have to do is yes. So, exactly. So, for that what you have to do is you can simply take A to be G. If you take A to be G, then Ka will be whole of K. K will be whole of K, and then you will see that the order of K divides order of G. So, Lagrange's theorem is indeed a special case of that. So, this kind of argument that we have seen earlier. So, now the same kind of argument we can also see here. The reason for that is indeed a generalization of the previous one. Okay. So, now we are going to exploit, we are going to consider an important application of this. So, as I said, important application of this. All right. So, as expected, we take as usual, yeah. So, let J be a finite group, P be a prime, and let us say P to the power K and order of G is P to the power Km. So, P be a prime and k be some integer. Note that I do not insist that this has to be the maximum power of p dividing order of g. So, p be a prime, k be an integer, k be a positive integer and m be a positive integer, and g be a group having order p to the power k m. That is all we are considering now. So, yeah. Now, what we do is we consider the following collection of subsets. So, we consider all subsets having order p to the power k, okay. All subsets of p to the power k, and we have already seen that for any such a, the stabilizer of A under G, because this set G acts on this set. So, this is by symmetry. So, if A has having order p to the power k, GA will also have p to the power k, because FDG by left multiplication gives us a permutation of G. So, this must divide order of A, right, just an immediate application of this. So, this is p to the power k. So, this could be either p to the power k or could be less. So, that based on that we define the following subsets just purely based on that. So, such that stabilizer of whether this has order p to the power k, and on the other case we consider only those subsets whose stabilizers is less than p to the power k. So, that is of the form p to the power l for some, okay. So, clearly S is nothing but the disjoint union of S and S prime, and it is obvious to see that G has action on S naught, because very simple that GA. So, GA will have stabilizer, the stabilizer of for any small g in capital G, GA, the stabilizer of GA will be a conjugate of the stabilizer of A. So, they are going to have the same order. So, G has a natural action of S naught and S prime as well, and S naught prime as well, and based on that we can say the following. So, what we do now is very simple. S, so S is the disjoint union of S naught and S naught prime. So, this will be S naught prime. Now, we break this as, because G acts on S naught prime. So, the order of S naught prime will be the sum of the orders of the disjoint orbits, okay, disjoint orbits of the action of G on S naught prime, okay. So, what does that give us? So, particularly, so let me write it for you, sum orders of distinct orbits, orders of distinct orbits, or orders of distinct orbits of this action, okay. Now, look at a non-trivial orbit of under this action. So, let B prime, so this be here. So, now consider the order of the orbit of this B. Certainly, this will be order of G divided by order of the stabilizer, okay. Now, order of G is p to the power k m. Now, the order of the stabilizer has to be some p to the power some power of p, but that power is not exactly k, right, because if you take anything here, yeah, so if you take anything in the stabilizer of B, since B belongs to here, the stabilizer of B is going to have order less than p to the power k. So basically it will have something p to the power l, but l is less than k. So that implies that Pm divides order of B, okay, Pm divides order of B. Therefore each of these terms here, each of the terms here are divisible, each of these terms here is divisible by Pm, hence one obtains, so let me write it here, so one obtains that modulo Pm, okay, good. Now we will go ahead one step further. So we now see, so yeah, so we now try to see what this quantity is. So for that let us observe the following, that if A is in this S naught, if A is in S naught and x is a point in A, then what happens to the stabilizer of A, so what happens to this right coset? So of course this has to be inside A, right, because the stabilizer. Now the thing is this has order p to the power k, so this coset has order p to the power k, this is a subset of A is also having order p to the power k, therefore now we must have equality here. Okay, we must have equality here. So thus we have seen that so if A belongs to this S naught, A must be a right coset, A must be a right coset of a subgroup of order p to the power k. That is all we have seen, that if A is in S naught, then A must be a right coset of, A must be a right coset of it must be a right coset of of a subgroup of order p to the power k. Conversely, if H is a subgroup of order p to the power k, then so this right coset has also order p to the power k. We now check whether this belongs to S naught or not. So for that we need to consider the stabilizer. So what happens to the stabilizer? So we see that, so this is fixed by H, right, because a small h, capital Hx, it has to be Hx, it's easy to see. So thus we see that this coset, right, this is contained in, H is contained inside that, and as a result of that its order, since H is contains, its order has to be p to the power k. Okay. Now on the other hand, what we have just seen is the stabilizer. So on the other hand, we have earlier seen that the stabilizer of a set, of a subset, divides the order of that subset. So again this is p to the power k. So therefore we got, this must be at most p to the power k, because it is dividing p to the power k. So, from these two it follows that stabilizer of Hx is having order p to the power k, and H is also having p to the power k. So, yeah, so in H is also having order p to the power k. So, therefore, stabilizer will be equal to H. So, there will be equality, but however, the important part is it has order stabilizer as order p to the power k will be equality yeah, but the important part is this is a subset of order p to the power k whose stabilizer is also having order p to the power k. So, therefore, this lies in S. So, thus what we have proved is if H has order p to the power k, then every subset, every right coset of H lies in S naught. So, let me summarize this and that. So, whenever a subgroup of p to the power k is given to us, whenever a subgroup of order p to the power k is given to us, is any right coset is going to be inside S naught, and every element of S naught, every subset belonging to S naught must be a right coset of a subgroup of G having order p to the power k. So, therefore, now we can clearly say that S naught is the collection of all right cosets of all subgroups of order p to the power k. S naught is the collection of all right cosets of all subgroups of order p to the power k. So, that tells me the following, that if now yeah, so let n be the number of subgroups of G having order p to the power k. Remember, we begin with a prime p and two integers k and m such that and a group of order p to the power k m. Okay. We begin with a prime p and a natural number k and another natural number m such that natural number m and a group having order p to the power k m. Yeah. So, we have these many subgroups of order p to the power k, and for each such subgroup how many cosets do we have? We have m number of cosets, right, because for any, I mean, the set of a number of left cosets and number of right cosets are same, all this we have seen earlier. So, for each such subgroup we have exactly m number of distinct right cosets. So, thus what we obtain is this S naught, that which is appearing here is nothing but m times m, implies that nm congruent to S yes. So, nm congruent to S naught prime, yeah, sorry, just made some, yeah, sorry, here I made a mistake, thank you. Okay. So, therefore, what we obtain is congruent to nm. So, let me put it in this way, is divisible by pm, and then that further shows that of course this has to be divisible by m is congruent to n modulo p. Okay. Remember here n could be 0. Okay, I do not know whether there is any subgroup of p to the power k or not. Okay, that I do not know. What we have said that if even this S, this S naught, that also might be empty. that we do not know whether it. So, if so all the argument is if this happens then that happens in that way. So, this could be in principle empty, that we do not know a priori. Okay. So, this is what we have got. So, this is, so what is this quantity? Order of S. So, S was the set of all, S was the set of all collection of all subsets of order p to the power k. So, when G has order p to the power k m, it is the collection of all subsets of order p to the power k, that collection has order p to the power k m, choose modulo p to the power k. So, the upshot is this depends on only on P, K and M and nothing else. So, it does not depend upon the group which we have considered. Okay. Let me again explain what we are having. So, given a prime P and two natural numbers K and M, then if G is a group of order this, the number of subgroups of G having p to the power k is congruent to this quantity modulo p, and this quantity is the fixed quantity, does not depend upon the group G. So, for any such group the number of p to the subgroups of order p to the power k is, for any subgroup, for any group G, its number of subgroups of order p to the power k is congruent to this quantity which depends upon p k m only. So, in particular if we take G to be the cyclic group, in principle if we in particular if we take G to be the cyclic group, then certainly for cyclic group this n is 1. So, this quantity there we find congruent to 1 mod p. Okay. So, now try to understand for any group G the number n, or you may write it simply, if you wish you can write it Ng for the time being. For any group G, Ng is congruent to this quantity modulo p, and we have already checked that this quantity is congruent to 1 modulo p. So, putting them together for every G of the above type we must have Ng is congruent to 1 modulo p. Okay. The main point is this quantity is independent, this quantity does not depend upon the choice of the group. So, whatever group we take, Ng is always congruent to this fixed quantity modulo p, and then later on we see that this fixed quantity is congruent to 1 modulo p. So, putting this together Ng is congruent to 1 modulo p. So, thus in particular Ng cannot be 0. Okay. And so, what have we obtained? We obtained that. So, what have we obtained? If G is a group and P be a prime such that, and P be a prime and K be a natural number such that p to the power k divides the order of G, then G has, then the number of subgroups of G having order p to the power k is congruent to 1 modulo m. So, in particular it assures that there is a subgroup of order p to the power k. Let me again summarize that. P be a prime, P be a prime, K be an integer, and G be a finite group. Such that order of G such that p to the power k divides order of G, then of course there exists a subgroup of G having p to the order p to the power k and furthermore the number of such H is congruent to 1 modulo P. Okay. This is all what we have seen. So, if P to the power k divides order of G, then the number of subgroups of G having order P to the power k is exactly 1 modulo P. In particular, it is at least 1. So, there is at least one subgroup of order P and number of this congruent to 1 modulo P. Okay. So, thus we have proved the other two theorems of Sylow. So, this is called the Sylow's first theorem. So, what is the statement of the Sylow's theorems? So, Sylow's first and third theorem says as follows, that if P is a prime, K is a natural number and G is a finite group such that its order P to the power k is dividing order of G, then there is a subgroup of G having, so G has a subgroup of order P to the power k and number of such subgroups is 1 modulo P. So, this is the first theorem of Sylow, first Sylow's theorem, and this is the third theorem. Second theorem we have already talked about, that says, so for the second theorem, so here the difference I would like to point out is, for the first and third theorem, k need not be the P to the power k need not be the highest power of P dividing order of G, that need not be the case, but for second theorem indeed it is required. Indeed it is required for the second theorem that the power must be highest power of P, that is dividing order of G. So, it is also quite natural to make the remark that if there is not the highest power, then what can we say at most. So, that is let me remind. Okay. So, in the proof of second theorem, what we obtained is, so K is a stabilizer of some H, right, for some H, this is contained inside H, and both H and K having the maximum order, yes. So, having let me put it in this way, what we can do is the following, that if H is a, so let just we are reviewing the proof, let us say H is, suppose H has order, well I think in the beginning I should say that so let order of G be P to the power k times m, where P does not divide m, and let H be a, okay. So, let me make a definition that whenever see these things happen, then any subgroup of G having order exactly P to the power k is said to be a Sylow P subgroup of G. Okay. So, by a Sylow P subgroup means it is a subgroup having order the maximum power of P dividing order of G. So, H be a Sylow P subgroup, H be a Sylow P subgroup. So, the second theorem, so in view of this terminology we can restate the second theorem in this way, that any two Sylow P subgroups will be conjugate to each other. So, the first theorem says that there is indeed a Sylow P subgroup, and the third theorem says that number of Sylow P subgroups is congruent to 1 modulo P. So, now come back to the remark regarding the second theorem from Sylow, and suppose K be just a P subgroup. So, that means is K has order some P to the power L, where L is less or equal to M. Okay. I can't say it is a Sylow P subgroup, I can simply say it is a P subgroup, that is order having some power of P. Then of course, as earlier, if we review the proof of the second theorem from Sylow, where both K and H both are Sylow P subgroups, there we consider this action. So, that action can be taken even if this L is strictly less than, even if this L is less than strictly less than K, right. And the similar argument goes, that is K will be contained inside, okay, for some A. That argument also goes for some, that argument also goes. And if now K is a Sylow P subgroup, then this being a conjugate of H having the order p to the power k, this is if K is a Sylow P subgroup, then K will also have order p to the power k, then they will be equal. Otherwise, if that is not the case, we cannot go anything beyond that. So, what we just obtain here is, if H is what we just obtain here is that any P subgroup of G must be contained in some Sylow subgroup of G. So, again try to understand, H has order p to the power k, so H is a Sylow P subgroup, being a conjugate of that, this is also a Sylow P subgroup, okay. This is also a Sylow P subgroup. So, thus what we have obtained is, if K is a subgroup of having order some power of P, then K must be contained in some Sylow P subgroup of G, okay. So, thus the subgroups of G having some order some power of P, they can be found inside the Sylow P subgroups. All right. So, enough. So, thus we have proved the Sylow's theorems. We will see many applications, standard applications of Sylow's theorem later on. Before that, let me now talk about another So, let me now talk about the other action, other way of other action of G on itself, namely by conjugation. So, yeah. So, all this follows from all this what we have seen regarding Sylow's theorem, that actually comes from the action of a group G on itself by left multiplication, and for right multiplication we do not need to actually bother, because that is isomorphic to left multiplication. So, another way in which a group can act on itself is by conjugation, which we will consider now. So, yes, then what we can do is, yeah. So, let me, so here let G be a group. So, G acts on itself by conjugation. So, we have already talked about that, so for each x in G, its orbit under this action is called a conjugacy class. We sometimes write it by this, or some authors simply write this by this. So, conjugacy, no, this is a problem, maybe we should not use this notation. So, this is a conjugacy class of H, and thus what we can immediately see is when G is finite. So, for G is finite, under this action, the class equation looks like this, that first the fixed points will come. So, under conjugation actions, the fixed points are precisely the points in the center plus the non-trivial orbits, and yes, non-trivial orbits, orders of the non-trivial orbit, orders of non-trivial conjugacy classes. This is how I can, in this situation, the class equation takes this form, non-trivial conjugacy classes. Okay. So, we have seen an application of this when G was a P group. So, by a P group I mean for a prime p by a p group I mean a finite group of order some power of p. So, when G was a p group we see that since all these non-trivial conjugacy classes their orders are divisible by p. So, then this is also divisible by p, but this cannot be 0 because identity is there, hence the center has to be non-trivial. In fact, so if G is a p group and H is normal in G, then also we can we have seen that plus the same kind of thing, which also assures that this quantity is at least p. So, so what we obtained is for any p group and any normal for any p group and any normal subgroup yeah. So, non-trivial normal subgroup. So, if H is a non-trivial normal subgroup of P, then H intersects the center of H intersects the so H intersects the just a minute just let me just make sure that so we can consider the okay. So, we are considering the action of G action of G on H because H is normal subgroup. So, action of G on H by conjugation makes sense here. So, every non-trivial normal subgroup of G intersects the center non-trivially. In fact, something more can be said here just from this, something I would say general. So, like this the argument of G on a normal subgroup. So, let me rather write this. So, let G be a group, let G be a finite group and P be the smallest prime. So, here I do not require G to be P group, P be a smallest prime P be smallest prime dividing order of G, okay. And let us say H is a normal subgroup having order P, okay. So, since H is a normal subgroup we do have the similar consideration, we can consider the action of G on H by conjugation. That is because that is it is I mean it is possible because H is normal, and then if we write the class equation we must have this kind of thing. Plus some of the usual terms. Now, so each non-trivial orbit here. So, G is acting upon H. So, the non-trivial orbits have so what can we say from here? Then let us first see. So, can it have a non-trivial orbit? Because orbit, so order of an orbit divides, so order of an orbit divides the order of the group which is acting. So, therefore, we okay. So, maybe since I am running out of time, let me just simply write down the conclusion, that is better. So, the point is like earlier we can immediately argue that this is divisible by yeah. So, this is divisible by P. So, I am leaving the details to you to figure out. This is also divisible by P, and since and since because this will be non-trivial, once non-trivial, so it should have a prime divisor. So, P since P is the smallest prime dividing order of G, so P must divide this, and from that again it follows that H should be contained inside center of G. So, if you have a normal subgroup having ordered the smallest prime dividing G, then that normal subgroup must be contained inside the center. And since I do not have time, so I am leaving this the justification from this step to this step to you. That is an easy one, the usual one. Okay. And I will say just one more thing, and with that I will finish. So, in fact, I think that I mentioned that under this conjugacy action, the stabilizers are called centralizers. So, for any x in G, the stabilizer is called the centralizer. So, it is denoted by this. It precisely contains all elements G in G, so that G x G inverse equal to x, and yeah. So, thus we see that the class equation in this way takes this form. So, here A 1 up to A k, I from 1 up to k, A 1 up to A k are the representatives from the distinct conjugacy classes. Okay. So, with that I will finish. मुझे कहा गया